Hey everyone, and welcome to The Explainer. Today we're doing something pretty exciting. We are building a true architect's blueprint for crafting reliable, production-ready AI voice applications. We're going to take some incredibly dense technical documentation, forum discussions, and research papers and break them down into a clear, layer-by-layer guide from modern voice AI.
But first, think about this for a second. What actually happens when your AI voice agent just stops talking? We've all been there, right? That super awkward, endless silence on the other end of the line where you're wondering if you should hang up or say hello for the 5th time. The truth is, a voice agent is exactly like a chain. It's only as strong as its weakest API call. And when that link snaps, the entire user experience collapses.
So, here is our roadmap for The Explainer today. 1. Building modern voice agents. 2. Upgrading the conversational brain. 3. Mastering text-to-speech economics. 4. The power of fallbacks. 5. Automating live product demos. And finally, 6. The future of voice.
Section 1. Building modern voice agents.
Look, building this architecture isn't just about plugging in a shiny new AI model and calling it a day. It's a real engineering puzzle that requires stitching together old-school telecom infrastructure with cutting-edge software, all while keeping the system safe and reliable. That means we have to define a bit of heavy telecom jargon right up front. Take a SIP trunk. Basically, it's just a virtual version of a traditional analog phone line. As the Create.ai documentation points out, enterprise systems integrate these virtual numbers with their AI voice gateways. It lets you seamlessly route voice traffic over the internet, connecting legacy phone networks straight to your modern AI stack.
Section 2. Upgrading the conversational brain.
All right, let's move to the next layer. The brain of our architecture is what processes speech and decides what to say next. And wow, we've seen a massive leap in quality here recently that's solving some major headaches for developers. Take the stark contrast between Gemini 2.5 and 3.1 Flash Live, based on production reports straight from the Google AI Developers Forum. Developers using 2.5 were plagued by these random 1011 resource-exhausted disconnections. Total nightmare. But with the migration to 3.1 Flash Live, the leap is massive. Lower latency, way more natural responses, and a huge relief for developers. Literally, 0 unexplained disconnections.
Now, it's not totally foolproof yet. You'll actually hear this phrase echoed around the developer community quite a bit. Turn 1 works, turn 2 dies. The production reality behind this is super fascinating. If a developer pauses their mic but misses sending the specific audio stream end event, the server's voice activity detection just gets stuck waiting. It times out and the user is left listening to total dead air. The brain is perfectly fine, but the communication protocol failed.
We also see platforms like Retail AI aggressively upgrading this brain layer over time. Peeking at their change logs, you see a massive dashboard overhaul in late 2024, followed by an AI QA analyst in early 2026, and dynamic voice speed controls shortly after. And importantly, they're keeping reliable support for GPT 4.1. They've introduced wild features like manual emotion tags, where you can literally type out sigh in brackets, and they've enabled WebRTC auto-reconnection for sessions up to 14 minutes, all while dropping prices to just 10 cents per minute. That kind of economic viability is genuinely incredible.
Section 3. Mastering text-to-speech economics.
So once the brain decides what to say, it obviously needs a voice. Let's talk about text-to-speech economics. Synthesizing voice is notoriously expensive, heavily rate-limited, and honestly, it's usually your biggest bottleneck for scaling. Take this real-world frustration from an Olbersoft GitHub issue. They were using Azure's free FO tier. Out of 467 total calls in a 24-hour window, they hit 29 HTTP 429 rate limit errors. That is a 6% failure rate purely from API quota limits. For a live voice agent, a 6% failure rate is just completely unacceptable.
And this brilliantly illustrates a really clever engineering workaround. By swapping in the Edge TTS Sharp 2.0.6 library, developers literally bypass that quota problem altogether. Edge TTS offers 100% free access to Microsoft's high-quality neural voices, including specific check voices, with lightning-fast 2 to 3 second generation times. And the absolute best part? It requires 0 API keys.
Section 4. The power of fallbacks. But hey, what if Edge TTS suddenly goes down? What if your user speaks a language it doesn't support? This brings us to the safety net architecture. According to Grokipedia's breakdown of dubbing scripts, you need an elegant fallback sequence. Step 1. You attempt your primary commercial API, like 11 Labs, which has incredible emotional range. Step 2. Your system actively monitors for HTTP errors, like a 400 or 429, or checks for an unsupported language code. Step 3. Upon failure, you seamlessly switch your request to a secondary fallback, like mms-tts. This ensures a single API failure doesn't just crash your entire production pipeline.
The crucial point here is having a safety net wide enough to catch absolutely anything. That is where Meta's open-source mms-tts model comes in. Through the Hugging Face VITS model, this thing natively supports a massive scale of over 1,100 languages. You don't need custom model training for low-resource languages anymore, making it the ultimate, massively multilingual backup plan.
When you compare these text-to-speech providers side by side, the production reality gets very clear. 11 Labs gives you perfect fidelity and emotional nuance for around 70 languages, but you're paying a commercial premium. Edge TTS sits right in the middle as a fantastic, free, standard option. And backing them both up, mms-tts handles that massive long tail of over 1,100 low-resource languages, ensuring absolutely no user gets left behind, even if it does come with a non-commercial license restriction.
You can even apply this exact fallback concept at the enterprise telecom level. Core.ai's voice gateway handles failures beautifully using system error settings. If the AI completely crashes, the system automatically sends a refer to SIP header in the SIP request. This literally forwards the caller's line straight to a fallback phone number, making sure they seamlessly reach a human agent without the call ever dropping.
Section 5. Automating live product demos.
Okay, so we have a resilient brain, a cost-effective voice box, and bulletproof safety nets. Let's look at the completed building with a futuristic real-world application from PayPal AI, a multi-agent pipeline called Redder. It's designed to replace expensive human presenters. It doesn't just read a script. It takes a live, running web application and its source code as input. It explores the UI, reads the code to understand the architecture, writes a script, and then actually rehearses the presentation in a headless browser before ever going live. And this solves a massive problem with traditional demo automation. If you've ever tried to sync AI voice to an MP4 video, you know all about word offset drift. Basically, variable API latency causes the voice to drift completely out of sync with the visuals. RHETR fixes this by ditching the video entirely. Instead, it enforces a strict runtime synchronization invariant. It triggers the next visual action only when the narration literally finishes speaking using a server-client handshake tied directly to the audio_end event. The sync is absolutely perfect.
And the metrics totally prove it works. During RATR's pre-presentation rehearsal loop, it validates every single semantic locator it plans to click. If an interface element has drifted or changed, the system repairs it offline. By the second iteration of this rehearsal loop, the system's internal locator firing rate converges to a perfect 1.00, meaning every single planned click executes flawlessly during the live, voice-narrated demo.
Section 6. The future of voice.
So, what does this incredibly complex blueprint actually mean for the future of building voice apps? Well, what we've learned today is that a truly resilient stack requires careful management from top to bottom. You need your AI brain set to a minimal thinking level for the lowest possible latency. You absolutely must manage for telecom protocols with explicit audio stream end triggers to prevent dead air. You need multi-tiered TTS fallback mechanisms, and, as we saw with Rhetor, you can combine all of this to power real-time, perfectly synchronized experiences.
Which leaves us with one final, challenging question for you to chew on. Is your voice architecture actually ready for the real world? It's so easy to build a demo that works perfectly on your laptop, but as we've seen today, scaling it requires a tight integration of telecom routing, API economics, and rock-solid safety nets. So check your weakest links, review your fallbacks, and make sure your agent never stops talking. Thanks so much for joining me on this explainer, and I'll catch you in the next one.